Hello guys, this is Mathematics for AI Research. If you understand and learn the math I'm gonna explain in this video, you will be able to take any AI research paper and understand math within it as well. And you will be able to continue doing research in any part of AI that you wish. So is it large language models, transformers, video generation, diffusion, image generation, reinforcement learning, robotics, whichever part of AI you are interested in, this is fundamental math that appears in everywhere. This is gonna be part of my course on creating and training large language model like Kimi K2 thinking from scratch, but this math applies to the entire field. Whichever AI research you are doing, you're gonna have to be learning this math as well. If you click the first link below this video, you're gonna get to this repository, Become Elite AI Researcher, and the first module is math, which is what I'm gonna explain now. We have all of these Jupyter notebooks. So requirements here is that you understand basic Python. So here we have some array, we have some for loop, we have some variables. So this is all basic Python. So if you are not familiar with basic Python, you can just type a Python tutorial on YouTube and you can check whichever one you like. Maybe this one, or actually Harvard classes are actually very good. So I want you to know how to execute Python code. It can be on your local machine or it can be in Google Colab. So now I also want you to say Google Colab tutorial if you want to use Google Colab, but also you can just run it on your local machine. So whichever one you prefer. Also, if you're using VS Code or Cursor or some fork of VS Code, you can install this brand new Google Colab extension. So if you just search for Colab, it's by Google, install it, and then you can connect to Google Colab GPU, CPU, TPU from your local environment, from your local Jupyter notebook. So now on my GitHub repository, in the math folder, I want you to open this first Jupyter notebook. So you can copy this and open it in Google Colab. As I explained, you can ask ChatGPT how to do it or open it in your local or however you want to open this. And then I have it here on my local and we're gonna go through this. So if you install Google Colab extension, you can click here Google Colab and we can say open Google Colab web, but I don't want to open this on web. I want to say select kernel with which to activate this and select another kernel and then Colab. And then I can create new Colab server and then I can choose CPU in this case because I don't need to run this on GPU. But keep in mind, now you can write a name. I can just use the default name like this, press enter, but you don't actually need to do this if you want to run the Python code on your local computer. So I'm showing you how to run it from your local using Google Colab, Google's GPUs or CPUs, but you can just run it locally as well. And so if I click here Colab, I can click remove server if I want to shut down the server. But anyways, first, depending on which kernel you are running here, if it's Google Colab, it will have these NumPy, Matplotlib already pre-installed. But you may also want to create your own environment. And this is something you would learn how to do on YouTube or from ChatGPT, and you need to install these requirements. So if you try to run this, but you get error like NumPy or NP is not defined, then you don't have these requirements installed. So make sure you enter your console and make sure you are in the folder where in which the requirements are. So this is the outside folder in which requirements file is. And then I'm gonna say pip install -r requirements.txt, but make sure to create your environment. Install this in a Python environment and then just press this. Enter. But actually, I don't want to install PyTorch because for the PyTorch tutorials, I'm gonna use Google Colab. So I'm just gonna install NumPy and Matplotlib and then I'm gonna comment out PyTorch. So let me do the installation again. Okay, now this is already installed. So let's start with the maths. Now that you have everything set up, everything installed, I will show you the curriculum. First, we're gonna learn the functions. So these are math functions, not Python functions, but math functions. Then derivatives. then vectors, gradients, matrices, and probability. A lot of you may already be familiar with some of these, especially maybe with functions, but you can use timestamps below or chapters to skip, but maybe you can also watch it anyways. So function will map from one value or from one set of values, but let's make it simple. You have some value x equals 1, your function will transform it into some other y, like y equals 2, based on some rules. For example, if we have function that y is equal 2 times x, then if x is 1, y will be 2. If x is 5, y will be 2 times 5 is 10. And I want to draw this so as x goes 0, 1, 2, 3, 4, the y is going to be the double. So here, at, for example, at 5, y will be 10. So then for every x, we're going to take and draw corresponding y. So for example, for 2.5 right here, y will be 5. For 2, y will be 4 right here. For 5, y will be 10. So if we then just connect all of these dots, we draw all of these dots, we get this line. So this is a linear function. And this is how we drew. This is where the plot drawing happens. So you don't need to understand this part at all. This is just to show this plot. So let's just understand this part. This is our function. So we will create an array of x values between 0 and 10. And we're going to create 100 x values between 0 and 10. Which is including 0 and 10. So you see we have x from 0 to 10, and in between we have 100 small dots. And for each of these, we're gonna just calculate the y corresponding y values. So 2 times these x values. So y will also be an array of 100 numbers, but each element will be 2 times the corresponding element in the x. So if it's 3, it's going to be 6 here. 4 will be 8, etc. And then we just use this to draw. And that's how we draw the linear function here. And let's see if instead of having number 2 here, we have some other numbers. So y is equal to 1x, 2x, 3x, 0.5x, minus 1x. So this number will determine the slope of this linear function. The 3x, which is the highest number here, will also have the highest slope. The lowest number, minus 1, will have kind of highest negative slope in negative direction on negative x. For example, if we look at y equals x, here where x is 4, y will also be 4. So then that's this slope as well. And the way this is coded is very simple. There is a list of k values, and then we just plot for each of the k values, we plot the function. I recommend using AI, ChatGPT or Cursor to explain any of these things for you if you don't understand it. But I want to focus on the theoretical part of the math for now. So this coefficient determines the slope of the function. Then there is quadratic function, where y is equal to x squared. So as we go on x slowly, the y will become a lot bigger, will start to accelerate. So in the beginning, y doesn't grow so quickly, but later, when we go from 2 squared, 3 squared, 4 squared, 5 squared, the y starts to become a lot bigger, a lot faster. Here, like 0 squared is 0, 1 squared is 1, 2 squared 4, 3 squared 9, 4 squared 16, so y starts to grow very fast. You can play around with this code to see and to modify it to see what the drawing will look like. Now notice that y is always positive here, so y never goes down below 0 on y-axis. We never go down because square function, quadratic function, will always make everything positive, because if you multiply two negative numbers or negative number with itself, it's going to become a positive number. So if you square a negative number like -2 here, it will become a positive number. But that's not true for the cubic function, where putting a negative number cubed will give you negative number. So this is what cubic function looks like, and it grows even faster than square function. Here at 3 we are already at 27 on y, and 3 was just 9 in the square here. So cubic grows even faster, but there is also negative part of it. So this is the shape of the cubic function. This is the shape of the square function. So knowing these shapes is good. Square root function. So y is equal to square root of x. I'm gonna have the same code here, so I put some numbers. You can only find roots of positive numbers, by the way. You cannot find roots of negative numbers. It's not defined, or it's not real, I should say. And so this is what y equals square root of x looks like. This is also good to know, this kind of function. It's growing very fast in the beginning, but then it's starting to grow slower and slower. Although this will grow to infinity as well. So there is no limit here. It will also grow forever. As x grows forever, y will also grow forever. Then we have exponential function, where y is equal to 2 power x, or some number, some constant power x. And this grows very fast. This grows faster than the quadratic. So 2 power x grows faster than x power 2. It's good to know that. And this is the shape of exponential function. The code is very similar. This part is just different. So y is equal to 2 power x. This is how you can denote power in Jupyter or Python. We also have sine functions. So y is equal to sine x. And I'll show you first that this is a periodic function. And this function is important. It's a trigonometric function. It's used everywhere. It's used so often. And in Python, you can just write y is equal to math.sine of x. Now let's go back to the linear function. So this is also a linear function. So we have some 2 times x, which is coefficient and the variable, plus some constant or minus some constant that doesn't have times x in it. Or so if you change this number 3, make it 4, 5, 6, you will just move this function left or right. So the slope will be same. So if you change this number 2, then you will change the slope of the function. But if you change this number 3, you will just move it left or right. This is also important to know. And now we may take a look at these functions. And so that's going to be math functions. I recommend you play with this. Make sure you understand this, and we can go on to the next lesson. Next we have derivatives. I'm going to try to explain the main points of derivatives. So if you have a function, you can find the derivative of that function that shows the rate of change of the function, how quickly it grows at each point. So you see, this linear function is always growing at the same rate. So this function is not like quadratic, where it's growing a bit slower here, a bit faster here, etc. This linear function is always growing at the same rate. In this case, the derivative is going to be equal to this number 2. So if we have 2x, the way I'll show you later how to calculate derivatives, but the derivative will be this 2. So at any point, when you increase x by a little bit, when you go in the x forward by a little bit, the y will go by 2 times that amount you went on x. So you move x a little bit, the y will go up by 2 times. So here you can see the derivative is 2 at any x. So at any x here the derivative is always 2. because it's a linear function, the growth is always the same. Can you try to explain yourself what derivative is? Can you try to explain what I just explained yourself? So derivative shows rate of change, and it's linear function, so rate of change is always the same, and it's 2 in this case. It's equal to this number 2 of 2x. So in my code, I have the function f of x, and the derivative is just hard-coded here. It's always 2, because I'll show you later how to calculate it, but this will be derivative 2. Let's see derivative of this quadratic function y is equal x squared. So the derivative here will be 2x. And I'm going to explain how it's calculated, but we can see that here the function doesn't grow equally everywhere. So actually, as we increase or go further into negative on x, the y will start growing a lot faster. Here around 0, x is growing, but y is not growing up so much. But as we grow x, the y grows a lot faster. So now we don't have a constant derivative that's always the same, like 2, the constant growth. Here we have derivative looks like a linear function. So the derivative here is 2x. So the derivative itself can be drawn as a function, by the way. So we have 1 and 2 for this spot. So funnily enough, you can also take derivative of this derivative. So that would be second derivative. So here the growth will be just 2. Derivative of 2x will be just 2. But let's not get confused. So here we have the function x squared, the derivative is 2x. Because the formula is you put this, so if you have x to n, you put this number 2, number n in front of x, so you get 2x. You just put this number in front of x, so you get 2x. And you subtract 1 from this number up here. So 2 minus 1 will be 1. So you will have x to power 1. So that's just x. So the derivative of this is 2 times x power 1, which is just 2x. That's the formula for calculating derivatives. You can also check other tutorials. Now this can go quite deep. I think it would be good if you knew it, but it's not absolutely essential to master this. I'm just explaining. These are the things you need to understand. You also learn this in high school. So you will encounter this in some research papers, and it's good to know this stuff. Now, do you want to dive deeper right now or later? It's up to you. So what this derivative means is that any of these points, wherever you pick x, for example, if you look at x equals 2, then that means here on this original function, if at x2 you increase x by just a little bit, then the y will increase by 4. You see here it's number 4. So if you increase x by a bit, the y will increase 4 times, because at this particular place, let's calculate derivative. Derivative is 2 times x, so 2 times 2 is 4. So at this particular place, if you increase x by a little bit, the y will increase 4 times that little bit of your increase. Here, at 3, derivative is 6. So at 3, if you increase x by a little bit, the y will increase 6 times that little bit. And so you can see that y is increasing faster and faster as you increase x. So this may require a bit of practice, a bit of maybe pen and paper. You can try to think about this yourself. Maybe watch some specific tutorials on derivation if you wish so now, or maybe even later. So we have this quadratic function, and I want to show you at each of these points, whichever points we pick, 0, 1, 2, on the x-axis, each point has its slope. So because it's quadratic function, we can see that there is no slope at 0. X equals 0, there is no slope because y is 0, x is 0 here. At 1, there is a slope. At x equals 2, there is even higher slope. So this slope is basically the derivative. I told you that at x equals 2, if you increase x by a little bit, so by 0.001, for example, the y will increase by 4 times that amount. Now, I'm not going to tell you that if you increase here x by 1, so you go from 2 to 3, the y will increase by 4, because I'm not going to tell you that, because as you move towards 3, the y rate of change will also be increasing. Keep in mind that the slope will change. That's why I say if you increase, so just around this 2, a little bit around this number 2, the slope is 4, okay? As you move towards 3, the slope will become 6, it will increase. So that's why I say if you just increase x by a little bit here, the slope will increase by this amount, 4 times or 6 times. But if you increase x by a bit, by a lot more, then the slope will also change. So in summary, the derivative will show you this slope, it will show you rate of change around this point. And for this particular function, the slope or the derivative will be equal to 2x. So here, if x is 1, the slope is 2. If x is 2, slope is 4. If x is 3, slope is 6, etc. Now let's see some derivation rules. So if you have x power 3, you're gonna put this 3 in front of the x, so the derivative will be 3 times x, and also you need to subtract 1 from this exponent. So 3 minus 1 is 2, so the final derivative will be 3 times x power 2, and it's just x power 2, so it's x power 2 times 3. And so you can see these examples, like derivative of x power 5 is gonna be 5 times x power 4. You just subtract 1 here, so it's x power 4 times 5. And this 4 is not like, it's not the whole thing, it's just x power 4. And so if we have a function y equals x cubed or x power 3, then the derivative will be 3x squared according to the rules. So this is the derivative function, it's 3 times x squared. And so we already know that x squared is gonna be like this U shape. We discussed that earlier. And then 3 times x squared, so it will just make the y's even larger. It will maybe squish it like, so this coefficient will just change this, how wide or thin the U shape is. But basically, because we have x squared, we're gonna have U shape. So that's the derivative. It shows how the function is changing at any of these points. Some other derivation rule. So if you have a function 2x plus 3, you can find derivatives of each of these separately. So around plus or minus, so you can find derivatives of 2x and derivative of constant 3. And the rule is that constant 3, any constant, becomes 0. So it will just be plus 0. So we can omit that. And derivative of 2x will be, so the rule is the following. If you have constant times variable, the constant will remain the same. So 2 will remain the same because it's times variable, okay? Here, this constant 2 is not separate. So here, 3 doesn't have any variable attached to it. 3 is not multiplying a variable, so 3 disappears, it becomes 0. But here, constant 2 is multiplying a variable, so it remains 2. In the derivative, this constant 2 will remain 2. It's explained well in ChatGPT. So as I said, derivative of a constant, it's a lone constant that doesn't multiply variable. Like here, 2, constant 2 multiplies variable. So this is not a lone constant. So if you have a lone constant doesn't multiply variable, then derivative is 0. So this part will be completely deleted, omitted. And then derivative of 2x is 2. Let's see how. So 2x is equal to 2 times x power 1. And we know that I explained earlier. that if we find derivative, so first of all, because we have constant times variable, we will just, this constant will remain the same. So in the derivative, this constant will not change. So in the derivative, this will still be 2 times something, okay? So now let's see what that something is. I told you the rule is, whatever power you have here, you put it in front of the x. So 1 will go in front of the x, and then you will subtract 1 from whatever power we have here. So we have 1 minus 1. So 1 times 1 minus 1. So that's 1 times x to 0. X to 0 is just 1. So this is equal to 1. Any number to 0 is equal to 1. So that's going to be 1. Okay? So then I told you, we will just get 2 times 1, because, as I said, 2 multiplies variable, so it remains the same in the derivative. And then we apply this rule x to the x that I explained, so it will be just 2 times 1. And so this derivative of 2x is 2. So at the end, derivative of this is 2, derivative of this is 0, so we get 2 plus 0. We get derivative of this whole thing is 2. So you can practice this. This is done in high school, university. You can practice this yourself if you want, with ChatGPT or some other AI or YouTube videos. And I can show it to you here. So the function is 2x plus 3. The derivative is 2. It's always 2 for any x. Whenever you increase x, the y will increase by 2 times whatever the increase in x was in this function, because the derivative here is always 2. So this means that plus 3 constant doesn't affect the slope of the function. As I said, the slope is determined by this number 2. And so if I change this number 2, the slope of the function will change. But this constant plus 3, this will just move the function left or right. So this constant plus 3 will not change the slope. So it makes sense that it disappears in the derivative as well. It becomes 0. It doesn't affect the slope. And now I just want to summarize derivative. So we have linear function, the derivative is constant. We have quadratic functions, so x power 2, the derivative is linear, so x power 1 is the derivative. We have a cubic function, x power 3, the derivative will be x power 2, it will be quadratic. So the derivative is kind of 1 degree less than the function. So that's going to be the core knowledge you need to know about derivation. You will eventually learn more as you read papers, but for now this is enough. Third lesson, let's learn about vectors. So this is maybe the most important one besides matrices as well. Everything is in vectors in machine learning, in neural networks. First, we will look at a vector as just an array of numbers. So here we're going to create a NumPy array. Hopefully you understand what NumPy is. You can watch YouTube if you don't understand this Python. So these are fundamentals. You can learn that first. So array of just 2 numbers in this case, 3 and 4. Vector can be array of any amount of numbers. And we can also look at these numbers as coordinates on a coordinate system. So x is 3, y is 4. We can look at that this way if we want. So this blue example, it's gonna be x is 3, here 3, and y is 4. So that's the vector, the spot. So we can draw a vector by going from 0 to that spot. And you can see that vector is like an arrow. So vector has a direction and length. Direction and length. We can also look at a vector as going like 3 units this way and then 4 units this way to end up at this spot. And here we have 2 other examples of minus 2, 1. So going minus 2 on x and 1 on y. Minus 2, 1. And 0, 5. So 0 on x, 5 on y. So this vector will be on the on the y-axis. Then let's look at vector addition. So if you have vector 3, 2 and vector 1, 3, if you add them, you're gonna say you add the first elements, so you add 3 plus 1, the first elements will be 4, and the second elements, 2 plus 3, will be 5. And we can also add vectors visually, starting from the first vector 3, 2, going from 0 to 3, 2, and the second vector 1, 3. Now, this vector would go here from 0, 0 to 1, 3 like this here. So this would be this second vector. And then we will just move this second vector to the end of this first vector if we want to add it visually. And so wherever it ends up, that's going to be our resulting vector. So the resulting vector will be 4, 5. We can draw it from origin to 4, 5 if we want. So that's how you can add vectors visually as well. Let's see multiplying vector with a scalar. So if we have vector 2, 1, what happens if we say 2 times that vector, 0.5 times that vector, minus 1 times that vector? So this blue is our original vector. So it goes from 0 to 2, 1. Now multiplying with a scalar will stretch or squish or inverse, so make it go in the other direction. So 2 times vector 2, 1 will give us vector 4, 2. So you multiply each of the elements. So 2 times v is going to be 2 times 2, it's 4, and 2 times 1, it's 2. So the resulting vector will actually be 2 times longer, and it will have same direction. And multiplying with 0.5, it will just make it 2 times shorter instead. Multiplying it with minus 1 will have the same length, just the opposite direction. So it will be minus 2, minus 1. How do we calculate length or magnitude of vector? How long is this vector? So it's actually similar to Pythagoras' theorem. So you can just say x squared plus y squared. You add them up, and then you get the square root of the result. But in Pythagoras' theorem, you just have 2 numbers. But here you can have any amount of dimensions. So you can have x squared plus y squared plus z squared plus a squared. So you just add all of the squares of every dimension. And at the end, you take the square root of that sum. So let's say we have a vector that has 4 dimensions. Let's say this is the vector. And then we just square each dimension, sum them up. Let's say it's 30, the square of the sum of all the squares. And then take the root of 30, and that's the length, the magnitude of your vector. So it's always the square root. It's not like 4th root here, it's square root always. Here are some examples. If we have vector 1, 1, the magnitude will be 1.41. So that's the length, the magnitude of the vector. So you can see here that this is a bit longer than this 1 unit. So it's about 1.41. Here, the vector 0, 5, the magnitude will be 5 here. You can already see that the length of this is 5. Okay, and then vector 3, 4, 3, 4, the magnitude, the length of the vector will be 5 units. And if you remember from Pythagoras' theorem, if you have triangle with sides 3, 4, the hypotenuse will be 5. But what's gonna happen often is if you have some vector that has some length, you will want to squish it back so it has unit length of 1. This is to make vectors in neural networks stable. They don't, because you are multiplying a bunch of them, so they're gonna start exploding. The resulting vectors will become exponentially or quadratically or a lot bigger and bigger and bigger as you multiply them, or they will become a lot smaller and smaller and smaller and vanish. So you will want to normalize vectors. You will want to make vectors of unit length, of length 1. Let's say we have a vector 3, 1. You will find its length which is going to be 3.16 in this case. And you will just divide this vector with its length, with its magnitude. And when you divide, so dividing it means you will divide each dimension with the magnitude separately. And then this new vector, it's gonna be unit length. So it will have same direction. It will just have unit length. It will not be, it will have be long one unit, whatever the unit is. So neural networks like numbers around 1 because when you multiply a bunch of those numbers, it will not the result will not become very huge or very small, which is not good for graphic cards. They cannot represent very huge numbers or very small, very big numbers or very small numbers. So you want to keep your numbers around 1, 0, -1, something like that. Now let's understand dot product. So dot product shows you how similar two vectors are. Here in this image, you can see that we have vector A and vector B. And these two vectors are closer together, so which means they are more similar than here, where there is 90-degree angle between them, or here, where they are very separate. So these two vectors are most similar. These are less similar, and these are least similar. Maybe I should say aligned instead of similar, but word similar is also used very frequently, maybe even more frequently. So it's very simple. We will multiply first dimensions. So here we have a vector, let's say 3, 4, and the second vector is 1, 2. To find dot product or similarity between them, we multiply 3 times 1. So we multiply the first dimensions, and then we say plus multiplying second dimensions 4 times 2. Okay, so 3 times 1 is 3 plus 4 times 2 is 8. So 3 plus 8 is 11. So dot product between these two is 11. So if our number is positive, like 11, then they are pointing in the same direction. Okay? If the two vectors are perpendicular, 90 degrees angle between them, then the dot product will be 0. Okay, so if you get the dot product 0, you know that these vectors are perpendicular, and this is useful in muon optimizer. This may be the new way to make neural networks learn a lot faster, better. I'm gonna talk about this in a different part of the course. So just know that if vectors are 90 degrees between each other, they will have dot product 0. And if you have dot product 0, that means the vectors are 90 degrees. And if dot product is negative, then the vectors are even further away than 90 degrees between them. So they are even more different or dissimilar. In Python, we can calculate dot product by just calling np dot dot v1, v2, vector 1, vector 2. So vectors v1 and v2 that we calculated manually have dot product of 11. Now these two vectors, 3, 4 and -4, 3, have dot product of 0, which means they are perpendicular. So v1 and v3, you can see that the angle between them is 90 degrees. So they are perpendicular, so dot product will be 0. And then v1, v4, so v4 is actually -3, -4, so the blue and the yellow, they are very different because they point in very different directions, opposite directions. So their dot product will be like negative number, -25. It's gonna be large negative number here because they are very different. Subtracting vectors is very easy. If you have vector 4, 3, you wanna subtract vector 1, 2, you will just subtract each element from each. So 4 minus 1, that's gonna be your first element, which is gonna be now 3. And the second element will be a result of 3 minus 2, which is gonna be now 1. So the new resulting vector is 3, 1. We can also show that visually. So if we have this blue vector, which is 4, 3, and we have a red vector which is 1, 2, we can draw a vector from the end of this one to the end of the first one, and then move it back to the origin. And that's gonna be our new vector, which is gonna be 3, 1, our resulting vector. So you will start from the second vector that you are subtracting, going to the end of first vector from which you are subtracting. That's your new vector. So then you can move it to the origin to see its real coordinates. And that will be it for vectors, and see you in the next lesson. Let's talk about gradients. Let's say we have some surface like this. So at any point of this surface, you would want to know in which direction to move to go up, in which direction to move to go down. This is used in neural networks to know if, for example, this surface would show error. So you want to make error small. So you want to go down on this surface. So how do you, in which direction to move to go down on this surface? Now I know if you've never heard of loss function and in neural networks, then this is confusing, like how is this showing an error? But we will talk about this later. But just know that if you have some surface, you're gonna use gradients to know which way you need to move to go up, which way you need to move to go down. Because the gradient will show you the direction of the steepest ascent. So in this direction, if you want to go up fastest. So that means that in the opposite direction, you're gonna go down fastest. For this point where you are standing, so very near around that point. So that's what gradients are used for. For every point on the surface, they show you in which direction it's ascending, increasing. And so in neural network, we will just go in the opposite direction to decrease, because in neural network, it will be used to represent, this surface will be used to represent our error, which we want to minimize the error. And gradients are closely related to derivatives. You know that derivatives are showing you the slope. So in gradients, you will also use derivatives to see the slope, but we will use partial derivatives. So let's see what those are. In this case, we have a 2D surface, so 2 dimensions. We have x dimension and y dimension. And we want to take partial derivative with respect to x and partial derivative with respect to y. So what does that mean? So if we stand at any point, if we just move, let's say, on x direction, positive x direction, we increase x 1, 2, 3, 4. Do we go up or down on this surface? So we want to examine if we move on x. So when we change x, do we go up or down? Are we ascending or descending? So that's going to depend on where we stand at the surface. So we will take partial derivative of this function, this loss function or this surface, with respect to x at that particular, so we will know, so when we plug in our particular x coordinate in which we are currently standing into that partial derivative with respect to x, we will know if, for example, when we increase x, if the function will increase or decrease. So that's the partial derivative with respect to x. And it's partial because there is also y. So we have 2 partial derivatives with respect to x and with respect to y. So then for that same position where we calculate if we increase x, does the loss increase or decrease? We will also calculate for y. If we increase y, does the loss increase or decrease? So if we find that as we increase y coordinate, the loss will increase, then we want to go in the opposite direction. We want to move in the y decreasing direction. So if, let's say, this is y increasing, we want to move in the y decreasing, so the loss will also decrease as we move. So that's in the case if we find that partial derivative with respect to y is such that when we increase y, the loss is increasing, okay? And it works the other way around. If we find that if we increase y, the loss is decreasing, then we just want to keep moving in that y direction. And so the x direction and the y direction will give us, well, the gradient at that spot will show us the direction of the steepest ascent, steepest increase. So we will just go in the direction of the steepest decrease, the opposite direction. So these are gradients. We're gonna see some examples to learn more about this. You can also check some YouTube videos. This may take some time, a few iterations, a few times of you understanding this to finally grasp it. Gradient will just be an array of numbers. And the first number in this array will be partial derivative of the function with respect to x. So it's just a derivative. So if we increase x, what's the change in the function? What's the slope? So it can be 1, 2, 3, minus 1, minus 2, or minus 1.5, or whatever the number is. So we have a derivative of the function with respect to x and derivative of the function with respect to y. And I should say partial derivative. So that's the gradient. So if we have a function x squared plus y squared, here these arrows will show you the direction in which it's increasing most from that particular point where you are standing. So x squared plus y squared will look like this. It will look like a ball, And so here at the bottom, there will not be too much of a slope. So these arrows will be small. The magnitude, the length will be small because there is not too much slope. But as you go to the sides, the slope will be higher, larger. And so the magnitude, so each of these vectors will show you how steep it is. And it will also show you the direction in which it's steep. The longer the vector, the longer the gradient, the steeper it is. And it shows you direction in which it's steep. So if you want to move down, then you would go in the opposite direction of this arrow. If you are standing at this place, you want to go down, you want to go opposite. This is why it's called gradient descent in neural networks. You want to go opposite of the gradient. Because gradient shows steepest ascent, you want to go down the loss function. This is what x squared plus y squared looks like. It's like a ball. Now let's see how to calculate gradient of a simple linear function, 2x plus 3y. We have two variables. So first, in our gradient, the first element will be partial derivative of x with respect to the function. So we will treat y as a constant. If you remember in derivatives, when we treat y as a constant, then this whole thing will be a constant, so it will become 0. It doesn't multiply x, because right now partial derivative with respect to x will just treat x as the variable. So now we will just have 2x as the derivative of this. Oh, sorry, 2 as the derivative of this. And then when we do partial derivative of the function with respect to y, then we just treat y as the variable and x as a constant. So we have 2x, that's a constant. That whole thing is a constant, it becomes 0. So derivative of 3y will just become 3. So here we have partial derivative of a function with respect to x is going to be 2, and partial derivative of the function with respect to y is going to be 3. So it's just gradients and derivatives. In this case, we don't have any variables in the gradient, so we just have constant 2 and 3, which means for this function, the gradients will always be same. It doesn't depend on x or y. The gradient is always the same. So these arrows are always going to be the same. This function will always rise in this way. It's like a plane. It's always the same. Always rising in this way for the same amount is like a plane. But if we have maybe a curvy surface like this, so this surface is x squared plus y squared, we will notice that at the bottom it's a bit flat, so there is no so much rising or ascending or ascent. So the vectors, gradient vectors, will be smaller, but as we go up, these values will grow quadratically, they will grow faster and faster. So as we increase x and y values, the slope will be bigger and bigger and bigger. So these gradient arrows will become larger and larger. As I said, the gradient will show the direction of steepest ascent. So if we have this function x squared plus y squared, if we find first of all the gradient, there is gonna be 2x comma 2y. So gradient partial derivative with respect to x will be 2x, partial derivative with respect to y will be 2y. So our gradient for this function will be 2x comma 2y. I can show you here. The function is x squared plus y squared. This is how you can write square in Python. The gradient will be just 2x and 2y. So for, let's see some point like 0.21, so x is 2, y is 1. We're gonna get 2 times x is 4, 2 times y is 2, 2 times 1 is 2, so our gradient at 0.21 will be 4,2. 4,2 will be our arrow right here, but it's not shown fully. But anyways, it points to the steepest ascent, so we want to take the opposite arrow to point it at the descent, how to go down the function. Now let's learn about matrices. This is extremely important. This is how neural networks work. This is the main thing about AI neural networks. So this is a matrix. It's an array of arrays. Okay, so you can look at this first row as one array. So 1, 2. This is the one array. And then the second array is 3, 5. So that's one matrix. So each of these numbers has its index. So starting from 0. So this is the 0th row. So the first row is actually has index 0, just like in normal programming. This is a row with index 1, okay? Column with index 0, column in index 1. And so this element has index 0, 0. And then this has 0, 1, 1, 0, because this is a row. So first it's row 1, and then column 0. So 1, 0, and then 1, 1. So if you want to add two matrices, you just add each element, corresponding elements at the same index. So 1 plus 2 is 3, 2 plus 5 is 7, etc. This is how addition works. Matrix multiplication is the most important operation in neural networks, in machine learning, in AI. So you have two matrices. First of all, this number of columns here, 3, must be same as the number of rows here, 3. So this 3 and this 3 must be same. So we have 1, 2, 3 columns, 1, 2, 3 rows. If you swap these places, you will get a completely different resulting matrix. So you cannot swap places of matrices and get same result. You will not. That's a different operation. This is how you multiply two matrices. So you do a dot product between this row and this column, and they must be same length. So 3 times 0 plus 1 times 2, this is the classic dot product, we talked about this earlier in the video, plus 0 times 0, okay? That's the formula here, 2. So that number 2 goes at the intersection. So it's gonna be first row and first column, so first row, first column here. That's this dot product result. And then you will go for the second one, you go first first row and second column here. So you go 3 times 4 plus 1 times 2 plus 0 times 1, and result goes here. So you just put the result at the intersection. So first row, second column, first row, second column. And at the end, you will get a matrix that's size of these outside dimensions. So 2 times 2, because this middle dimension will cancel out. And this middle dimension must be same, equal. And this outside dimension, outside doesn't have to be same. So if this was 2 times 3, this matrix and this matrix was 3 rows and 4 columns, then it's possible to multiply because 3 and 3 inner dimensions are equal, and the resulting would be 2 times 4 if this was 4. In Python, you would define matrix as an array of arrays. So this is the first row, this is the second row. Here it's being indexed as 1, 1. So here indices are starting from 1, maybe to show like example for you to understand it easily, but usually indices start from 0, 0. First row, second row. Just like here. So this is the first row, this is the second row. And this has 2 columns as well. So 2 rows, 2 columns. And so that's how we can define matrix in Python with, for example, NumPy. We can also do it with PyTorch and stuff. And this is example of 3 by 2 matrix. So 3 rows, 1, 2, 3, and 2 columns. Now these rows and columns are gonna take some time for you to understand intuitively quickly what's happening. Like 2 by 3 matrix, 2 rows and 3 columns. So we can print shape of the matrix. So A matrix, it's this one. So shape here is 2 by 2. And then we can print shape of the first row and shape of the first column. So let's see. Shape is 2 by 2, rows 2 and columns 2. It's maybe easier to understand on this example because here rows and columns are different shapes. So shape is 2 by 3, rows 2, columns 3. So if you say print a dot shape 0, that's gonna be the first number in your shape. So it's gonna be this number 2. And shape 1 of 1 with index 1 will be the second number 3. Maybe you want to play with this a little bit to see what happens. So this is going to show the number of columns, this is going to show number of rows. And so if you have a matrix 1, 2, 3, 4, 5, 6, you can access individual elements by just calling the index. So this index of this would be 0, 0. So if you say A of 0, 0, that will give you this value, which is in this case the value is 1. If I put it like this, it's going to be 10. So this value has index 0, 0. And that's how you can access the elements. I'm actually going to talk more about this indexing and slicing later. It's more for maybe PyTorch tutorial. So let's go on to matrix addition. I already explained this. So here you would just add each element with corresponding on the same index. So 1 plus 5 is going to be 6. The resulting will be 6. And then 2 plus 6 result will be 8. So same index. Scalar multiplication, you just multiply. So if you say 2 times matrix A, you will just multiply each of these elements with 2. So this will become 2, 4, 6, 8. So let's see the result here. 2 times A, you will just multiply with 2, or 0.5 times A, you will just multiply each element with 0.5. 0.5, 1.52. Minus 1, same, just each element with minus 1. Matrix vector multiplication is just like matrix multiplication. So you first need to make sure that the inner dimension is same. So 2 times 3, so this 3 must be same as this 3 times 1. In this case, you can multiply A matrix multiplied vector V, but you cannot multiply vector V matrix multiply vector A, because then this inner dimension would not be same. So you can first put this first and then this second, and then that's how you can matrix multiply it. And then the result will be 2 times 1, because the inner same dimension will cancel out. And the step-by-step calculation goes like this. 1 times 2 plus 2 times 3 plus 3 times 4. And then that's going to be 20. And then 4 times 2 plus 5 times 3 plus 6 times 4, that's going to be 47. So that's the resulting vector. So you multiply this row with this row. Now this could be a bit confusing because I was showing you that you multiply row and a column. But depending on how you do it, how you code it, how you imagine it, this can also be done this way, because this is just a vector. So in matrix multiplication, the way we imagine it conceptually is row times column. But since this is just a vector, we can also imagine this as a column vector, being 2, 3, 4, and then this row and this column vector. So this is a bit confusing. You're gonna have to do this by yourself, by hand. Try to multiply, try to figure out, try to get intuition. Try multiplying this, try multiplying others, maybe get some other examples from AI, from ChatGPT. So the matrix multiplication example here, I explained it. So you can use this at as matmul, or you can use np dot, which is a bit confusing because this implies dot product, but this is actually, this is matmul. And so here you have step by step on how to multiply two matrices, but this is just something you would need to understand. And I saw Sam Altman explaining something about matrices, and he was showing this with his arms or hands. So that's how I know that he also knows how to multiply matrices. I was wondering if it was in his job description as CEO of OpenAI to be able to multiply matrices. I was always wondering that. This is transposing matrix. So we have 1, 2, 3, 4, 5, 6. We transpose that, it becomes, so we swap rows and columns. So it's now, this column now became the row. So 1, 4 now became the row. 2, 5 now became the row. And the shape is swapped now. Then we have identity matrix, where it's 1 on the diagonal and others are 0, and it's a square matrix. It has equal number of rows and columns. And when you multiply any matrix with identity matrix, it will remain the same matrix. So the result will be the same as this matrix that you multiplied with the identity matrix. And in Python, you can create identity matrix by saying np.i and then how many rows and columns. So 2 or 3 or whatever the number is. So this is the 2, this is 3 by 3, it can be any number. So identity matrix acts like the number 1 in multiplication, so it doesn't change the thing it's multiplying. Here are some properties. You can analyze them if you want. I just want you to understand that in matrix multiplication, you cannot swap the order of matrices. This is not generalizable. It's not true in general. There might be specific cases when it's true, but in general, it's not true. That's gonna be it on matrices. If you understand this, you understand everything you need to know about matrices as your fundamentals. So let's check out the last lesson as well. Lastly, let's learn about probability. This is extremely important. It's used in large language models, reinforcement learning, computer vision, natural language processing, everywhere. So you have a coin. Let's assume it's a fair coin. You flip it, you have 50% chance to get heads, 50% chance to get tails. Or you roll a dice, 6 sides, so you have 1/6 chance for any particular side to appear, to be rolled. Probability measures how likely an event is to occur. 0 means impossible, 0% chance probability. 1 means certain, 100% chance of probability always happens. And 0.5 means 50-50. So let's calculate probability of flipping a coin and getting heads. So we have 2 possible outcomes, heads and tails. But we are calculating probability for just one of those outcome, heads. So we say heads outcomes can be just one of those 2 divided by the total outcomes, which is 2, which is gonna give us 1/2 or 0.5 or 50%. So for rolling a dice, it's same. We just have 1/6 now because 1 side out of 6 possible. But in this case, we are assuming that each of these 6 sides has equal probability to happen. So then you can divide 1/6 to get your probability. Same goes for heads. If each of the heads or tails has equal probability, then you can divide. Here, if we flip the coin 10 times, we get 7 times head, 3 times tails. So theoretical probability is 0.5, but actual probability, measured I should say, is 0.7 or 70%. But as we flip more coins, the measured probability will get closer and closer to theoretical. So for 100 coins, we get 0.39, and for 10,000 coins, we get 0.5024. So this one, experimental, is very close to the theoretical. So the more flips or more samples, the experiment probability, measure probability, will get closer to the theoretical. And so if we try that with dices, we will get with 1,000 rolls, we will get close to the theoretical of 0.1667. And here the orange one shows theoretical probability of each dice face, and it's always the same, but the measured one, it's gonna be a bit different. But if we do a lot more measurings, then this measured one will get closer and closer to the theoretical. Now, what is the chance that if we roll 2 dices, one dice gives us 1, and the second dice gives us 6. So it doesn't matter which dice gives which number. We just need to get 1 and 6. And the probability there would be by multiplying those two probabilities. So it's gonna be a lot smaller probability to get both of them. Now, what is the chance that in those 2 dices we get 1 or 6, but not both of them, just either 1 or 6. So it can be 1 on the first dice, or 1 on the second dice, or 6 on the first dice, or 6 on the second dice. So there are 4 possible ways to satisfy this. But if we get 1 and 6, that's not what we want. So we will subtract the probability of getting 1 and 6, because that's not what we're looking for. And so the probability of getting 1 is this, and probability of getting 6 is the same. And then subtract if we get both 1 and 6, and this is the probability that we get 1 or 6 if we roll 2 dices. Here we have probability distribution. So this is the task. If we roll 2 dices, what is the probability that the sum of the numbers of each dices, like we get 1 and 6, so the sum is 7. So what is the probability of each of these sums? For example, if the sum is 2, it means we got 1 and 1. If the sum is 7, it means we got 3 and 4, and 4 and 3, and 2, 5, 5, 2, 1, 6, 6, 1. So you can see that we can get 7 in a lot more different ways than, for example, 2, because we can get 2 as the sum only if both of the dices are 1. But 7 we can get in a lot more different ways. So probability of the sum being 7 is a lot higher. And that's the probability distribution over all of these sums. So what is the expected value of a dice roll? We know that dice can show us numbers 1, 2, 3, 4, 5, 6. And each of these numbers has 1/6 chance to happen. So what is the average or expected number we will get by just rolling a bunch of times? You can maybe intuitively understand that the average number will be 3.5, because this is exactly in the middle of 1 and 6. But we can calculate expected value by multiplying the value we will get. So 1, 2, 3, 4 times its probability. 1/6 is the probability for each of these values. And then sum up. So sum up and divide by the number to find the average or mean. But this is very important. This summing up of all of the values and dividing by the number is just because every value has this equal probability to happen. That's why we can pull them into a bracket and then divide by this common denominator is the same for every one. But if these probabilities were different, not all are like same 1/6, then we would not be able to like sum up the values and divide by 6. So summing up and dividing only works if the probabilities are same. So that's like a shortcut you can do. But this is more general formula. You just do each value times this probability. And that's, but this is more specific. This works if probabilities are same. Then we have conditional probability. So probability of A happening given that B happened. You can calculate this by this formula. So probability of A and B divided by probability of B. It's easier to understand this in an example. So given that we roll an even number, what's the probability that that number is 6? So first of all, probability to roll an even number is 0.5 because we have 3 odd, 3 even numbers on a dice. And probability of rolling 6 and even. So you need to think a little bit. So if you roll 6, it will also be even. So here we're just gonna use the probability of rolling 6 because if we roll 6, it will also be even. So that's the probability. And so the formula, we intuitively know that, let's first look at intuition. So we have 3 of these. So if we roll an even number, then because each of these even numbers has same probability, then it's 1/3, 1/3, and 1/3 to be each of these numbers because they have same probability. So that's what we will get in the result, 1/3 or 0.3333. So, and if we check the formula, it will actually come out as 1/3. So the probability of getting 6 given that we got even number is 1/3. And this is the law of large numbers. So if you have probability, theoretical probability as 0.5, you're flipping the coin. In the beginning where you just flip maybe 10 times, maybe you will actually get 7 heads and 3 tails. But as you flip more, the measured probability will converge towards the theoretical probability. So that's the law of large numbers. If you have large numbers, they will converge towards theoretical probability. Now this is also interesting. Let's say you are tossing a coin 10 times. What's the probability that out of those 10 times you get 5 heads? I actually recommend you go to my channel and here in playlists you check out this Become AI Researcher Probability, because this is a playlist of going into probability a lot more in a lot more details, and you can check just first video or first or second. Those contain most important things. So random variable, standard deviation, variance, and then continuous random variable, probability density function. So maybe these 2 first videos you can check. That's gonna be it on this part on maths. You can join my school to become AI researcher, link below the video, or you can find it on my channel, here on my channel. Get a 7-day free trial if you join right now.